As we continue with our functions and their characteristics and understanding their shapes and names, we're going to talk about the extrema and the end behavior. And what we're going to talk about is identifying extrema of functions, identifying the end behavior, and these things we're going to carry forward throughout this course, and then being able to understand what these vocabulary words are. The extrema, that is the maximum minimum values of a function. And this isn't anything new. This is definitely when we talk about a quadratic equation or function, and we used it in algebra, we would look at this function right here, and we would say that's in a quadratic equation because of its shape, and this is the minimum point because it goes down. It has a negative slope, and then it turns around and has a positive slope. So this is my minimum, and then we start a quadratic equation that opened it downward. We would have said that this is my maximum point. So these kinds of things are not anything new per se. We're just looking at it a little bit differently, and we will talk about the relative minimums and maximums versus the minimums and maximums. So here, quickly identifying, I will say that identify and estimate the x and y values of the extrema to the nearest tenth, and I will just say that f of x here, it says the function is decreasing as it approaches, and then it is increasing. So there we have a minimum occurring at approximately 0.5. Approximately x is 0, y is 5. Looking at the g of x, and we are increasing, and then we turn around and we're decreasing. So this is a relative maximum point, and then this is, we're decreasing and then increasing. This is a relative minimum point. It is not a maximum or a minimum because this function continues to go on forever in a upwards and downwards direction. So that's why it is a relative max and min, versus over here, this was a maximum because it was ultimately the lowest point. And this one at the same time, I'm sorry, I said minimum because it was ultimately the lowest point. And this one has no maximum because it continues going on forever and ever. So that is understanding what my extrema in the sense of minimums and maximums do. Looking at this image, applying what is the purpose of it, or what does it mean? In this it says using a table and graph to estimate the extrema of a function that relates to the number of hours since midnight, x, to the number of posts being uploaded, y. So the time over the quantity of posts. Describe the meaning of the extrema in the context of the situation. Well, if hours since midnight, so this is midnight, and it looks like as we travel to 2 a.m., to 4 a.m., to 6 a.m., the posts decrease from midnight. Maybe people are going to sleep, and then we start to see an increase. Is it 4 o'clock? Is this because people are starting to wake up? And so we have an increase throughout the day because this would be 10 a.m., noon. Looks like at noon we have a maximum posting of number of posts, which would be approximately 11.5 hundred thousands. Then we have a decrease from maybe people are eating lunch or something is keeping them busy from the time of noon to approximately 2. At 2 o'clock we start to see another increase, and then at 4 o'clock it seems to be another increase, and then after 4, social media posts continue to decrease, until the next morning. So that's what we're being able to do, and we're being able to examine the understanding of maximums and minimums. So with that, exploring the end behavior now of these functions. The end behavior is going to be, in behavior is the behavior of a graph as x approaches positive or negative infinity. So as x approaches, this is my negative infinity, this is my positive infinity. And just think as the function keeps going this direction, so as my x's get larger, my y values are getting smaller because it's going to infinity, negative infinity, because it just keeps going down. As my x values go to negative infinity, my y values are going to a positive infinity. And that's what we want to be able to understand, is just where is it pointing and going. So as x decreases, right this way, f of x, or my y value, increases. And then as x increases, going this direction, my y values are decreasing. And this is, so as x approaches negative infinity, f of x approaches infinity. As x approaches infinity, f of x approaches negative infinity. And this is how we write that. G of x, now g of x, as x approaches positive infinity, as it keeps going this way, my function isn't changing. It is, y is the value of 2. As x approaches negative infinity, y is the value of 2. So as x approaches negative infinity, g of x is 2. As x approaches positive infinity, g of x is 2. So just being able to understand what we are looking at there. So in this, as x approaches negative infinity, as x approaches positive infinity, what is going on? Y approaches. So as we are going this direction, as x approaches negative infinity, y is decreasing. It is going down the y-axis, so it is getting to a smaller number, so that would be y approaches negative infinity. As x approaches positive infinity, y is approaching positive infinity. And there you go. That's understanding what the in behavior of my graph is doing. In behavior of nonlinear functions, what is going on here? We are, as in this case, quadratic equation. Again, as x approaches infinity, y is approaching infinity. As x approaches negative infinity, y is approaching infinity. So that's what we are looking at and understanding here. As let's see here, as x approaches infinity, y is approaching infinity. As x approaches negative infinity, y is approaching negative infinity and going downward. So there you go, looking at my in behavior. And again here, as x approaches infinity, as x approaches infinity, as x approaches negative infinity, y is approaching negative infinity because it is becoming increasingly negative. Y is approaching negative infinity, and it is actually doing it as x approaches negative infinity also. Y is approaching negative infinity. So there you go. And here again, trying to determine and interpret the in behavior of a function. The graph shows the altitude of a drone above the ground after x minutes. Describe the in behavior of f of x and interpret it in context of the situation. So over time and altitude. Over time and altitude. So it starts off when we launch the drone at 0, and then it travels up to approximately 120 feet. Then it comes down to, so let's see here, over time in minutes, like when I first start my drone, I launch it up into the air real fast, and then I start to maneuver, bringing it down in altitude, and then it goes back up in altitude. It reaches this maximum height of approximately 230 feet, and then it comes back down, and then it continues. So just thinking about what is going on with my drone and being able to understand the in behavior. So in this, the drone is expected to continue to go up. So realistically, will it go up forever? No, but just examining and understanding what the graph is showing me. And let's see here. Ride share, let's see here, what's going on? Micah and her friends are using a ride sharing service to take them to a concert. The function models the cost of the ride share after X miles, describe the end behavior of the function, and interpret the context of the situation. We cannot have less than 0 miles. So that's why they're saying f of x is not defined for less than 0, because we can't have negative travel time or travel distance. But as my miles increase to infinity, the cost is going to continue to increase towards infinity. So as x increases, y increases. So there's my answer. Again, this one is eliminated because we are not going to approach negative infinity. What does the end behavior represent in the context of the situation? How about the farther I travel, the more it's going to cost? So it just really depends on your interpretations. Now, sketching graphs and comparing functions. This is connected to what we've talked about for the continuity and the intervals and continuing on. So sketching graphs, understanding some of the key concepts here. Your domain, remember my x values, my y values, where I cross over the intercepts, the symmetry of a function in behavior, using my extrema, and then understanding the increasing and decreasing. And then the positive and negative is often overlooked here, but that is understanding when I'm positive, I'm above the x-axis. When I'm negative, I'm below the x-axis. So here in this, being able to interpret, looking at this function, I can see that my y-intercept is 0, negative 70. It appears to be a straight line. I can check the slope to see that. Positive for values, x is greater than negative 30. So right here, in this sense, where am I positive? That is where I have positive values at x is negative 30 or below, and then I have negative values when x is negative 30 or greater. So from this point, this direction, I have negative values. Let's see here, in decreasing for all values of x. So it is the slope, it is decreasing. And then my end behavior, again, as x approaches a positive infinity, y is approaching negative infinity. As x approaches negative infinity, y is approaching positive infinity. So understanding what those terms are and what they look like. Now, using those key features to go ahead and graph it, this is nonlinear. So let's see what we got here. It tells me the y-intercept is 0, 3. It is nonlinear, but it is continuous, okay? It's positive for all values of x. So that means nothing is going to be graphed down here because it is positive for all values of x. Decreasing for all values of x such that x is less than 0. All right, so it's decreasing until x is 0. And then the minimum is 0, 3. So I guess we're going to have increasing at this point in time. The end behavior is as x approaches infinity, y approaches infinity. Sure enough, I got that. As x approaches negative infinity, y approaches infinity. I got that. So that's what my graph would look like. Not drawn to scale, no specific points except for that y-intercept that we know about. So just being able to make those determinations and interpretations. Sketching a real-world function. So Hay is test driving a car she is thinking of buying. She decides to accelerate to 60 miles per hour and then decelerate to stop to test its acceleration and brakes. It takes her 15 seconds to reach her maximum speed and 15 additional seconds to come to a stop. Use the key features to sketch the graph and show the speed y and function of x. All right, so she decides to accelerate to 60 miles per hour. So we know that she is going to come up to 60 miles per hour, and it takes her 15 seconds to reach her maximum speed. So time is 15 seconds. 15 seconds. She accelerates from 0 to 60 in 15 seconds to reach her maximum speed and 15 additional seconds to come to a stop. She stops at 15 additional seconds. So that is sort of seems like what's going on here is she starts at 0 seconds and 0 speed. She accelerates to 60 miles per hour in 15 seconds and then decelerates to 0 speed in 30 seconds total. Extrema, let's see what's going on here. The y-intercept is going to be her starting point. It is a nonlinear function. Hay increases speed at a uniform rate for the first 15 seconds. It doesn't tell us otherwise, so here's my straight line slope of increasing speed, decreasing speed at a uniform rate, and then my end behavior. She starts at 0 and ends at 0. So there is no end behavior because it doesn't continue to go on. So with that, again, being able to compare functions, use the table and graph to compare the two functions. So we have graphed here g of x, and oftentimes what I like to do is I will just graph the same function on top of it, the comparer graph. So I went ahead and graphed the points from the f of x table, and the x-intercept of f of x is going to be 3, right? And I can see that here that when x is 3, y is 0. The x-intercept of g of x is going to be -2, 0. And then f of x intersects the x-axis at a point farther to the right than g of x. So just being able to do those kinds of interpretations and understand what we're seeing. And so as we compare them, we're comparing the characteristics. The y-intercept of g of x, or f of x, the y-intercept is 0, -1. So 0, -1 would be right here. The y-intercept of g of x is 4, okay? And then g of x intersects the y-axis at a higher point than f of x. Again, just being able to understand and compare what we see. And let's see here, the slope of f of x. The slope of f of x, if we did the slope formula, I'll just take this and make this y2, y1, I'm sorry, that's x2, x1, y1. So we would have the slope is equal to -2 minus -3 over -3 minus -6. So I end up with 1 over 3. So that's how they came up with that slope. And then the slope of g of x is simply up 2 over 1, so 2 over 1. So each function is increasing, but the slope of g of x is actually greater than the slope of y of x. So it would look something like this. Again, we can see the slope is not as steep. And there we have it. So let's see here. Which statements about f of x and g of x are true? I'm going to make this easy on me again. I'm going to go ahead and graph this function. Ignore that one. 0, 0, -2, 1 and 0. 2, and 2. So it looks like I have this function going on right here. That is my f of x function. So what do I know? G of x has a faster rate of change than f of x. Nope. F of x is steeper. That is not the case. The x-intercept of g of x. The x-intercept of g of x is greater than the x-intercept of f of x. That is true, because it is a larger number. The y-intercept of f of x is greater than the y-intercept of g of x. The y-intercept of f of x is a lower number than g of x. Both functions are decreasing. That is not correct, because f of x is increasing with a positive slope. F of x increases while g of x decreases. That is a true statement. And then f of x has a faster rate of change than g of x. That is a true statement. So there you go. Again, just being able to look at the characteristics of my functions, and then comparing properties of nonlinear functions again. Thinking about comparing nonlinear functions, and they've given us g of x right here, and what I've done is I've tried to highlight some of the characteristics of what they're giving us for f of x. So as I look here, they have, it's not drawn to scale, and it is an estimate, but at negative 3.4 we have a x-intercept. At 0, 1.5 we have the y-intercept. They tell us we have a relative maximum at approximately negative 2.3 and 4.7, and then a relative minimum at negative 0.4 and 1.1. And then my end behavior is x approaches negative infinity, y approaches negative infinity, so we're heading down. As x approaches positive infinity, y is approaching positive infinity. So this function would look something along the lines of this. Just sort of connecting my dots. Okay, not drawn to scale, obviously, but general motions. So I can see that comparing the x-intercepts, we have over here g of x. I have three x-intercepts. I can compare the y-intercept to g of x versus what we have graphed. The extrema, I can see that it has g of x has a relative maximum here, a relative minimum here. We have a relative maximum here and a relative minimum here. Neither one of them have a maximum or minimum because they continue to go both positive infinity and negative infinity forever. So there is not a maximum minimum. And then making what happened here. The x-intercept of f of x is blank any of the x-intercepts of g of x. It's less than, because it is a smaller x-intercept value. The graph of g of x intersects the x-axis 3 times. The y-intercept of f of x is less than the y-intercept of g of x. So g of x intersects the y-axis at, it looks like 1, 2, 3, 4, okay? Intersects the y-axis at a greater point, right? I'll just say greater, right? Using the greater point, than f of x, because f of x intercepts at 1.5. The relative maximum of f of x is, the relative maximum is going to be less than the relative maximum of g of x, less than, and then the relative minimum of of f of x, the relative minimum of f of x is actually greater than the relative minimum of g of x. And then the two functions have blank in behavior. They have the same in behavior, right? So that's it. Thus, just being able to look at our functions, using our definitions, and examining what's going on, and sometimes putting it in context. Carrying forward, this is how we, start to apply our knowledge and understanding into these algebraic functions in real-world situations.